Good morning, students. Am I audible?
Sir,
What is the number of participants? 20. Okay, in the last class, we have discussed about the average velocity, or you can say the distribution of velocity. So, what we have seen in the last class, our velocity, when we move from bottom of the channel to the surface of the channel, our velocity is also vary in this way. Okay, in the surface, it got reduced. And when we move from the left side to the right side or vice versa, then also our velocity changes. Here, due to friction, we have less velocity here also. And in middle portion, we have maximum velocity. Okay? As the velocity is not constant in a particular section, so when we talk about velocity head, or sorry, when we talk about kinetic head, when we talk about kinetic head, that is v square by 2g, that we have already discussed, as this velocity is not constant, we have to multiply by a coefficient that is called your energy coefficient, or you can say alpha. Okay, as this velocity is your mean velocity, so we have to multiply it by a coefficient that is called energy coefficient or alpha. And this alpha is varies from 1.03 to 1.36 for a fairly straight prismatic channel. So we have already discussed what is prismatic channel. So if we consider a prismatic channel, that alpha varies from 1.03 to 1.36. Okay. So because of this velocity, as this is not a constant velocity, this is your variable, or you can say it's a mean velocity. Mean velocity. So we have to multiply it by a coefficient that is your alpha. So when you talk about momentum, similarly when you talk about momentum equation, don't worry, we are going to discuss momentum equation in details in later classes. So this is your momentum equation. As this velocity, again it's not constant, so we have to multiply it by our coefficient. That is your called momentum coefficient or beta. So we have two coefficient. One is alpha, one is beta. Alpha is nothing but your energy coefficient, and beta is nothing but your momentum coefficient. Okay, and your alpha varies from 1.03 to 1.36, whereas beta varies from 1.01 to 1.12 for fairly straight prismatic channel. Always remember, whatever the value we are discussing is for prismatic channel. Okay, so here one table is given. Table 1.2, table 1.2. So they have given some values for alpha as well as for beta, with a minimum and maximum with an average also. Okay, for regular channel, natural streams. So we can consider those values directly, or we can calculate also. How to calculate, we are going to discuss next. Okay, so here you can see they have given some values. That minimum of momentum coefficient for natural channel is your 1.05 and maximum is 1.17, and they have taken average they have given 1.10. And similarly for river under ice cover, river valleys over flooded, so they have given some values for alpha, that is your energy coefficient. For river valleys over flooded, they have given minimum values of 1.5. So those things are standard. They have performed numbers of experiments, and they come up with these values. Okay, so sometimes we are going to use those values directly. Okay, so that it depends on what we are going to use. It we are going to use minimum or maximum, or we can simply use average also. Okay, so those values, they have come up with a very large number of experiments they have performed, and they, after all, after those results, analyzing those results, they have come up with these values for both alpha and for beta. Okay, so now how we are going to calculate that alpha? So there is a small derivation for alpha. So see, okay, so this is a cross section of a river. This is the bed of the river, or you can say boundary of the cross section. Okay, so this is the boundary. See, here what we are going to consider a small elementary area. That means we are going to consider a small area. We are going to consider a small area. Okay, okay. So the cross sectional area of the whole river is A, capital A. Okay, the cross sectional area for that particular small area is del A, or you can write dA. Okay, okay. The whole cross sectional area. That means if you consider this whole area, if you consider this whole area, consider this whole area, that will be your capital A. Okay. If you consider only that small area, that is your del A, or you can write dA. Okay. So, so here we are going to consider a del A, or you can say small elementary area of the whole cross sectional area A. So out of that whole area, we have considered a small area. We have considered a small area. Okay, small area. And your small w is the specific weight. So now we are going to find out the weight. So weight is nothing but your specific weight multiplied by del A. Del A means we are going to calculate this weight of that particular small area, or that particular small area. So that's why we have considered del A. If we are going to find out that weight for the whole cross section, then this will be capital A. So now we are considering only for the small particular area or you can say small elementary area. So that's why your specific weight multiplied by del A, that is small area, multiplied the velocity. So for that particular cross sectional, your average velocity we are going to consider capital V, and velocity inside that particular small area we are going to consider small v. Okay. So this is the weight, specific weight multiplied by area multiplied by velocity. Okay. So we all know mass equal to, sorry, so we all know weight is equal to mass into gravity. So if you want to find out mass, it's only weight by gravity. Okay. So here you can see this is your mass. Okay. So in place of weight, we have substitute this equation. Specific weight multiplied by area multiplied by velocity. So as we are considering here for that particular small area, so that is why we are multiplying specific weight with that particular small area, that is del A, multiplied by your velocity. Okay, in that particular small elementary area. That's why we have considered small v. Okay, so for mass, this is your equation. Weight by acceleration due to gravity. So now we come up with kinetic energy. Kinetic energy, we all know it is half multiplied by mass into v square, velocity square. So that is why half we have mass, and again we are considering the small particular area. So that's why your velocity is a small v, velocity square. Okay, so half mv square. So now here in kinetic energy, in place of mass, we are going to substitute this equation again. Okay, specific weight divided by acceleration due to gravity multiplied by del A, multiplied by del A, multiplied by del A, multiplied by velocity, and then this v square. Okay, so half, this is mass, this is mass, and this is velocity, velocity square. So this is kinetic energy. So here this is v square and this is v. That's why it will be v cube. Okay, others will be remain same. So now we have calculated the kinetic energy for that particular small elementary area. You can see here in this figure. Okay, this is the whole cross sectional area. This is the surface of water, or you can say level of water. So this is your small elementary area that we have considered. Okay, so now we have calculated the kinetic energy, kinetic energy for that particular small elementary area. Now, if we want to find out the kinetic energy of whole cross section, then what we are going to do, we are going to take summation of the kinetic energy for particular elementary area. That means suppose this is an elementary area, we can consider here number of elementary area. Okay, number of elementary area depending on the depth of flow. Okay, so suppose if this is your cross section, we can consider one elementary area here. This is one. Then we can consider another one. Then we can consider another one. Three, and then four, five, okay, and six. This is just an example. Okay. So now if we consider this is your small elementary area one, two, three of same depth, okay, of same depth. Then if we find out the kinetic energy for one, and if you add kinetic energy for 2, 3, and 5 till 6, we you are going to find out the kinetic energy for the whole cross sectional area. For the whole cross sectional area. Okay. If you find out one kinetic energy for one, then two, then three, then four, and five, and six, and if you add all the kinetic energy, then you can say that whole kinetic energy is for kinetic energy for the whole cross sectional area. Okay. That is why for the kinetic energy for whole cross sectional area, we are going to take summation. Okay. So in place of summation, you can take integration also. It's up to you. Okay. You can integrate or you can take summation. The same thing. Integration is addition. Okay. So here we have calculate the kinetic energy for the particular small elementary area, and then we have take summation. When you take summation, we don't know how many elementary areas we have considered. It depends on you. If you take, you may have considered only two elementary area by considering one is this and one is two. Okay. Or you may consider elementary area in similar way, one, two, three, and four. Okay. So it depends on you how many elementary area we you considered inside the channel. So that is why when you write summation, we will write I is to 1 n. So it will start from 1 till n. It may be 2, it may be 3, it may be 4, it may be 5, it may be 6, and so on. It depends on you how you are going to divide the whole cross sectional area, in how many numbers or in how many sections you are going to divide the whole cross sectional area. Okay. So it depends on you. So when you talking about kinetic energy for the whole cross sectional area, we are going to take summation. Okay. That equation will be same, only we will take summation. Okay. So our intention is to find out the alpha. Okay. Always remember what we are dealing here. Our intention to find the alpha or to derive an expression from which we can easily find out the alpha value, that is the energy coefficient. Okay. So here you can mark this equation 1. You can mark this equation 1. Okay. So now you take your whole cross sectional area. If you take the whole cross sectional area, forget about elementary area now. Okay. You take whole cross sectional area, and for that cross sectional area your mean velocity is capital V. Okay. And we know when we talk about kinetic energy head, we are going to multiply it by this alpha, as because this velocity is not constant, or you can say this is a mean velocity. Okay. So when you find out the kinetic energy for that particular cross sectional area, then what we are going to do, half into mass into velocity square. So again in place of mass we are using that equation. For the mass we using the same equation, but what we are going to now, we are considering the whole cross sectional area. So specific weight multiplied by total area. Okay. Because in previous case we have considered only the small elementary area, that's why we have taken del A or dA. Okay. So now we are considering the whole cross sectional area. So when we consider the mass. So we are going to multiply it by capital A. Then we multiply it by your average velocity or mean velocity. That is your capital V for the whole cross-sectional area. Then it's divided by acceleration due to gravity. So this is mass. Okay. So here. Okay. Then we have alpha. As this velocity is not constant or its mean velocity, we have to multiply it by alpha. So that is why this is alpha. Okay. So this equation is your total energy for your particular cross-sectional area. Okay. So now what we say, if this is your equation 1 and this is your equation 2, we can say that equation 1 and equation 2 is same, as because this is also your kinetic energy for whole cross-sectional area by considering some elementary area. Okay. And this is also equation 2 is also gives you the kinetic energy for the whole cross-sectional area. Okay. So your equation 1 and equation 2, both the equation you will give you the kinetic energy for the whole cross-section area. So now what we are going to do, we are going to equate equation 1 and 2. So we are going to equating equation 1 and 2. Okay. So here in left hand side, this small w is specific weight area into v cube by 2g, and we are multiplied by alpha as this velocity is mean velocity. Okay. In right hand side, we have considered from equation 1, from 1. Okay. So here you can see, here you can see we have specific weight. Here also we have specific weight. That will be cancel out. Okay. Then we have twice z here. Here also we have twice z. So these two will be cancel out. Okay. So what will be remaining? Alpha is equal to summation of v cube del a divided by v cube whole cross sectional area. Okay. So this is the expression for your alpha. This is the expression for your alpha. Okay. So in place of summation, you can consider your integration. Okay. So we will take an example of rectangular channel. Okay. So we will consider a rectangular channel. Okay. If this is our level of water. Okay. So this is your whole cross sectional area A. Okay. And your average velocity or mean velocity in that particular cross section is capital V. Okay. So now we are going to consider a small elementary area. Okay. In that particular small elementary area, your velocity is small v, area is dA. Okay. Area is dA, and what else? Your depth is dy. Okay. And you consider the whole depth is y naught. Whole depth of flow is y naught, and then for particular depth of that particular area, small elementary area is nothing but your dy. Okay. So now we are going to use this equation to find out the alpha for that particular rectangular channel. We are going to use this equation. Okay. So here alpha, again v by v whole cube dA by A. So dA is our small elementary area. So in rectangular channel, area is width into depth. So depth, as we are considering this dA, that is area of a small elementary area, so we have to consider the depth is dy. Okay. So that's why in place of dA, we have written b into dy. Okay. And divided by whole cross sectional area, here b into y naught, because the depth of flow for that particular cross section we have considered y naught. Okay. And this is your width of the channel, b, width of the channel. So if you consider a small elementary area here, the width will be same. Okay. If you consider a rectangular channel, the width of that particular small elementary area also be same. That particular area also be same. That's why your width will be same. And when you find out the area, if you consider the small elementary area, so your equation will be b into dy. Okay. A depth of flow for that particular elementary area. When you consider the whole cross sectional area, then it will be b into y naught. That is the depth of flow for that particular cross section. Okay. So this bb will be cancelled out. What will be the equation? Vy, this is the average velocity in that particular elementary area, then divided by average velocity for that particular cross sectional area, 1 by y naught dy. Okay. So this integration again, we have already discussed, it depends on how many number of section you are going to consider. It depends on you. So that's why your minimum limit is 0. Okay. And maximum is y naught. That means whatever the elementary area we are going to consider between 0 and y naught. Okay. So we cannot take number of elementary section beyond this y naught, because this is our maximum limit, as this is our depth of flow. Okay. So that's why here limit you can see it's from 0 to y naught. Okay. If you see the limit, here it's 0 to y naught. Okay. Okay. All students are requested to give your attendance in the chat box. Okay. Write your enrollment ID. Okay. All of you Write your enrollment ID in the chat box. Okay.
Hmm.
So, do you have any questions regarding this alpha? It is little bit difficult, you know. If it is an offline class, it will be better. But now we can't help it out. So, if you have any doubts or any way you have not understood, you can ask me now. Or you can, okay, Himal. What you are saying that if the rectangle, okay, channel is not rectangle. Yes, we have just taken an example of rectangular channel. We actually this is a general equation, okay, and whatever what we have taken this equation, this is for rectangular equation. As the rectangular section is easy to understand, that's why we have considered rectangular section. We can apply this equation for rectangular also, trapezoidal also, okay. Then your when we consider trapezoidal, then your this equation here, that area equation will be changed, okay. You are not going to get this equation, okay. This is only for rectangular, but this is your general equation. Whatever you are getting here, this is your general equation. You can use this equation in the rectangular also, trapezoidal also, circular also, okay. It's up to you. Then whatever the area you have considered, that equation it will change, okay. If you consider trapezoidal, then we are going to consider a small elementary area here. Then we have to take the area of that particular small elementary area by considering as a trapezoidal channel, okay, by considering as a trapezoidal channel, okay. So here, and when we consider this a value, then we have to consider the area of the whole trapezoidal section, okay. But this limit, you know, this limit will be same from 0 to y naught. If your y naught is the depth of flow, suppose if your depth of flow is 5 meter, then your limit will be from 0 to 5 meter. So why this limit is related to the depth? See, when you have y dy here, that means you are going to integrate this equation with respect to y. So this limit should be respect to y, okay. Always remember, okay, when you, I think you all know about this thing because this you thing you have already studied in mathematics, okay. When you do integration, and if you do integration with respect to the something, that limit should be relevant to that, okay. As we are integrating this equation with respect to y, so this limit goes to 0 to y, okay. That is your related to your depth of flow, okay. And if it is a circular, then this cross sectional area we are going to take our circular. So it doesn't matter. Okay. Rectangular channel, we have taken just an example. Okay. So this is our general equation. Okay. This is irrespective of any shape of the channel. Okay. But as we can see that the rectangular channel is most common and is easy to understand, so that is why we have considered rectangular channel. And this equation what we have derived, this is only valid for rectangular channel. Any more doubts? If not, then we will proceed. See, we are going to solve numericals related to this. Okay. So when you solve numericals, then it will be more clear. I believe. Okay. So, and if you don't understand anything about this, then it is very difficult to solve the numericals. Okay. So now we are going to proceed. Yeah, when we see this equation, or you can see that alpha equation for a rectangular channel. If you can see this V, to solve this equation, we need average velocity of that particular cross section. Suppose if we talk about rectangular channel, if you consider a rectangular channel, to solve alpha or to find out alpha, we need the average velocity V for the particular rectangular section. Then only we can solve this alpha. Okay. So how we are going to find out this velocity is our next derivation. Okay. What is our next topic is to find out that average velocity V, and by finding out this velocity we substitute that velocity here so that we can find out the alpha value. Okay. So that means if you are asked to find out alpha, first we need to find out the average velocity. Okay. Then only we can find out alpha, unless and until that velocity, average velocity value is given to you. Okay. If I specify that velocity is 1.5 meter cube per second, sorry, meter square per second, then you can find out the alpha. Otherwise, to find out alpha for a particular section, you need to find out first is that average velocity. Okay. So the next topic for R is to how to find out the average velocity for a particular section. Okay. So here you can see again, this is your cross section of a river, or you can say a irregular section. Then we have considered a small elementary area. The area of that particular small elementary is dA. The depth is dy, and this small elementary is at the depth of y from the surface. This is your surface. From the surface to that particular section that we have considered, this length is y. Okay. And the whole depth is, or you can say depth of flow, maximum depth of flow is y naught. Okay. So we all know when we travel from bottom to the surface, our velocity, it changes. Okay. And here it reduces. Okay. It's increasing, and because of this flow of air, okay, interaction between your flow of air and your surface of water, your velocity at the surface it reduced. Okay. So what we are going to do, similarly we are going to consider a small elementary area like the previous one, where the velocity v for that particular small elementary area and area for that particular small elementary area is dA. So now we find out the discharge. Discharge we all know, discharge is equal to area multiplied by velocity. This is known to us. Okay. So now we are going to find out the discharge for that particular small elementary area. That means we are going to find out the discharge in that particular area, small elementary area. So that discharge we are considered as del q or dq. It's up to you. Dq. So velocity we are going to consider small v for that particular area and multiplied by the area of the small elementary area. Okay. So dA. So similarly, previously also, if we find out the total discharge for the particular cross section area, for the whole cross section area, then we have to take summation or integration. Okay. So whatever we are going to calculate here, Suppose here we have considered one elementary area. It's up to you how many elementary area you are going to consider: one, two, three, four, five, and so on. If you add, if you find out the each discharge of each elementary area, and if you add all you have considered, then your ultimate result will give you the discharge for that particular cross sectional area. Okay, so if you add, if you take summation or integration, it will give you the discharge for whole cross sectional area, like the previous one how you have calculated. Okay, so you consider this is as equation 1. Okay, then if you want to find out the discharge for the whole cross sectional area, we can simply take discharge equal to area into velocity. Okay, so area into velocity. So again we are going to equate both the equation. So velocity will be 1 by a vda. Okay, okay, vda. So first we are going to find out the velocity using this equation. Then we go back to the alpha and we substitute the value of v here, and then we find out the alpha value. Okay, so when we are going to solve problems, then those things will be clear, how we are going to find out velocity, and then how we are going to substitute here, and you find out the alpha value. Okay, we are going to end today here. Okay, so tomorrow or in the next class we again discuss about this thing by taking some examples. So I request you to bring or be ready with a pen and paper, okay, to solve some numericals related to your alpha. Okay, so in the next class we are going to discuss your beta value first, like your momentum coefficient is similar to your alpha. Okay, need not to worry, almost same as your, the derivation is almost same as your alpha, that is your energy coefficient. So we are going to discuss about momentum coefficient, and then we are going to directly, we are going to solve some numericals related to your alpha, beta, and your average velocity. Okay. So I request all of you to be ready in the next class with a pen and paper. Okay, and with your calculator also, because I think it will be integration. No, you need your scientific calculator to solve those integration. Okay. So if you have any questions or any doubts, you can ask me now. Okay, we have another 2 to 3 minutes. Students, actually, I am busy in this week. Okay, Actually, I'm involving in tabulation work for your final students, okay, final year students. So whoever taken my class, no, actually in the ERP we don't have any option to add classes, okay. So they have taken my classes and they are going to add in my account, okay. So to give ratings for those classes, you have to go to my open channel flow, and then you can rate those class, okay. So don't confuse, because we can delete our class, but there is no option to add. Okay. So whenever I will take their classes, then again you have to go to their profile and you have to rate your class. Okay. Then only you are going to mark present. Okay. So in today's class, I have taken my class. So in this class, you can rate in my profile, and whatever your Rituraj sir have taken na, previous class, that also you have to rate in my profile. Okay.